So suppose that we have a continuous random variable. Let's take this one, continuous random variable x, and suppose it is this PDF. So this PDF is 1 over 1 plus x on the interval 0 to e minus 1. Take the open interval, get too close, doesn't really make a difference. If you have another random variable y, which is defined in terms of x, in this case 1/2 square root 1 plus x, let's find the PDF of y. So we're finding a function that describes the distribution of y, where y is a new random variable defined in terms of x. We did this before for discrete random variables, and it was easy. And the reason it was easy is because we just said, okay, let's use the PMF of x, which had all the possible values and their probabilities, and we just run them all through this function, and we see what comes out, and we just say, well, whatever the probability you had for x equals 1, you just put a 1 in there, you calculate this thing, and you get y equals something, you're going to get that probability for y equals that thing. You just might have to, you might have different x's that give you the same y, and you have to add the probabilities. Now that we're in the continuous case, this is much more difficult, because we can't run all the possible values of x through here, because there are infinitely many of them, and they all have probability 0, so can't do that. Too bad. We've got to do something more sophisticated. There's two ways we're going to have of doing this. And so let's do method number 1. It's called distribution functions, the method of distribution functions. So to do this, we're going to first find the distribution function, the CDF, for x. Then we're going to turn it into the CDF for y. Then we're going to take the derivative of the CDF for y to get the PDF for y. All right, so here we go. So remember, the PDF is the derivative of the CDF. So to get the CDF for x, I got to do an antiderivative here. Okay? So let's see, we're going to do this. So let's take an antiderivative of this guy, 1 over 1 plus x. There's no limits here. I'm doing an indefinite integral. I just want a function whose derivative is that guy. Okay. So how do I do this? Well, it's a typical case where you do substitution. Let's let u be 1 plus x. Then du is dx. And that way we'll just get 1 over u. That's going to be easier to integrate. So we have, what do we have? 1 over u and d. Okay, du. That's easy. So we're going to get ln of absolute value of u plus c. And if we put that back in terms of x, that's ln of absolute value of 1 plus x. C. Okay, so here's a function whose derivative is that. So this is going to be the CDF for our random variable x. However, we have the c hanging out. We got to figure out what that is. Well, that's actually pretty easy, because now we know that our CDF, let's write it over here to give myself more room. Our CDF is ln of 1 plus x plus c. Well, just look at this. Our PDF is this function on that interval. Okay. And when I say that, what I mean is the PDF is this function on that interval and 0 everywhere else. So in particular, the probability a random variable comes out to be smaller than 0 is 0. Right? And for anything bigger than that, it's non-zero. So a way to figure out our constant c is we can just say, look at it. Imagine the graph of our CDF. Just imagine it, right? When I get to this interval, 0 to e minus 1, this CDF, whatever it is, it's going to go 0, 0, 0, 0, 0, 0, 0, and then it's going to go somehow up to 1, and then it's going to be 1 forever from then on. But the important thing is I know those 2 points are on the graph, right? So I can use that fact to figure out this c. In particular, here I know that the point 0 0 is on the graph. I could also use the fact that the point e minus 1, 1 is on the graph, and I get the same answer for c. So let's just plug in 0, and we know that we've got to get a 0 out. And that'll tell us what c has to be. Okay, so this, as we were talking about, this has to be 0. So 0 equals ln of 1 plus c. I took away the absolute values because 1 is positive, right? When I absolute value 1, I just get 1. And ln of 1 is 0, so this just means c equals 0. Okay, great. So finally, we arrive at our CDF for x. It's just ln of 1 plus x. And by the way, I am not going to write the absolute values. Why not? Because I know that our CDF is this thing on the interval 0 to e minus 1. And all these numbers, when I plug them in here, they all come out positive. Right? The absolute value doesn't do anything, because when I plug these into 1 plus x, 1 plus 0 is positive, 1 plus e minus 1, anything in between always comes out positive. And if you want to write it out in long form, you can write it like this, right? So it's going to go, well, let's look at 0. If little x is less than 0, then it's going to be this thing, ln of 1 plus x. If 0 is less than or equal to little x less than or equal to e minus 1, and then 1 if little x is bigger than e minus 1. Okay, so there it is really in long form. That's the CDF of x. All right, so all that to get the CDF of x. Now, how can I use this CDF and this method of distribution functions to get the distribution of y? Here we go. Watch this. Here's the trick. The CDF for y. All right? It's the probability y is less than or equal to a thing. Let's call that thing little y. But y is 1/2 root 1 plus x. So here, for this capital Y, I'm just going to put what it is in terms of x. 1/2 root 1 plus x. Great. And now all I'm going to do is I'm going to try and isolate the capital X here. Watch me go. Multiply both sides by 2. Square both sides. It's 4 little y squared. You got to be a bit careful here when you square both sides, making sure that when I'm dealing with inequalities especially. But everything here is always positive, so we're okay. Because this expression right here, if I think about plugging these values into it, right, it's always going to come out positive. Okay? So it is really true that if this thing is less than or equal to that thing, then when I square it, yes, it's still less than or equal to that thing. Right? When you square an inequality, you got to be careful because, right, if I have minus 1, let's just think about this, right? Simplest example, maybe minus 2, that's less than minus 1, right? But then when I square both sides, I'm going to get 4 is less than, oh, that's not true. Okay, so you got to be careful with inequalities here. But I'm good because this thing was indeed positive, and I squared it. Everything's fine. Okay, so finally, one more step. X less than or equal to 4 little y squared minus 1. Boom. Okay. Now what does that mean? Fy of little y is the probability x is less than or equal to this thing. But the probability x is less than or equal to a thing, we know it, because we know the CDF. The CDF is the probability x is less than or equal to a thing, little x. Okay. So what's the probability x is less than or equal to this stuff? Well, the probability x is less than or equal to a thing is what you get when you plug the thing into the CDF. So I'm going to take this stuff right here, 4y squared minus 1. I'm going to plop it in right here into the CDF. So this is fx at 4y squared minus 1. Okay. So what happens when we do that? Well, in this expression right here, this little x, it's being replaced by 4y squared minus 1. So this is ln of, what was it? 1 plus 4y squared minus 1, which is just ln of 4y squared, right? Okay, great. However, just make sure that this only worked when the thing we're plugging in, this little x, was between 0 and e minus 1. So in this case, it's going to be on the interval you get when I take all these values of x and I run them through this function. So 0 to e minus 1, let's run those through this function. This function, if you think about it, this is a one-to-one function. And I'm going to run all these through. It's an increasing function. Sorry, it's a better way of saying that probably. It's an increasing function. So when I run this interval through, what do I get? The numbers that come out are just, the lowest one is going to be when I plug in 0, and the biggest one is going to be what I have when I plug in e minus 1. So I plug in 0, and I get 1/2, right? I plug in e minus 1, and I get 1/2 root e. So this is going to be on the interval from 1/2 to 1/2 root e. Cool. All right. So, in conclusion, we now have that the distribution function of y, if you want to, CDF of y, if you want to write it out in this long form, it's going to go 0, 0, 0, 0, 0, just like CDFs do, 0, 0, 0, 0, then it's going to go up to 1. It's going to be 0 if little y is smaller than 1/2. It's going to be this thing, ln of 4y squared. If 1/2 is smaller than or equal to little y, smaller than or equal to 1/2 root e. And it's going to be 1 if y is bigger than 1/2 root e. Great. Okay. Cool. One thing to note, we talked about this before, it doesn't actually matter. You might think, oh, this is an open interval. Why is this? Might get hung up on this. It doesn't matter. If we put the less than there, when I plug in 1/2 to this, it comes out 0, whether I use this clause or this clause, right? If I put a 1/2 in here, 4 1/2 squared, 4 times a quarter, ln of 1 is 0. Okay, so it really, I could put that there, and I could put that equals there. It doesn't make a difference. It's the same function. So finally, this is a long one. We were looking for the PDF, the probability density function for y. We just figured out the CDF, the cumulative distribution function for y, and the PDF is the derivative. So finally, fy of little y, what is it? It's the derivative of this. And the derivative of this is 0. First clause, the derivative of this is 0, and the last clause, the derivative of this is the only part that isn't 0. So let's see, what is the derivative of that? It is the derivative of ln stuff, 1 over stuff, right? And then by the chain rule times the derivative of the stuff. So I think it's that, yeah? 1 over 4y squared times the derivative of the inside, yeah, 8y, which is equal to, the y's cancel, and I get 2 on top. Looks like 2 over y. Oh, nice simple thing, actually. If y is in the interval, this guy, 1/2 to 1/2 e. Great. So that was the method of distribution functions. So if you have a continuous random variable and you have a new one defined in terms of that one, you know the distribution of the old one. To get the distribution of the new one, what did we do? We found the CDF for the first one. That actually took a while. Then we did this trick where we realized the CDF for the new one is the probability it's less than or equal to a thing, little y, some dummy variable. And then we replace the capital Y with what it's defined to be in terms of x, isolate the x, and you realize this is just the same as plugging this value into the CDF for x, right? And so you do plug that value into the CDF for x, you see what you get, and that'll give you the CDF for y. Then I took the derivative of the CDF for y, gave me the PDF for y. All right, that took a while. So there's another method called the method of substitution, but I will save that for another video because this took a long time. So next video, method of substitution. It's a bit faster. Sometimes it's a lot faster.